The best the best example of the torsion in our domestic use, we squeeze the water from the cloth. We squeeze the water from the cloth. Means what is the meaning of that? कि वो जो क्लॉथ होता है उसको धुलने के बाद अगर हम हाथ से उसका पानी कैसे निकालते हैं, जो भी एक्स्ट्रा पानी रहता है, हम क्या करते हैं कि दोनों हाथ से क्लॉथ को पकड़ते हैं और उसको ट्विस्ट करते हैं अपोजिट डायरेक्शन में। एक हाथ आपका क्लॉकवाइज घूमता है, एक हाथ एंटी क्लॉकवाइज घूमता है, जिसकी वजह से क्या करते हैं कि क्लॉथ के ऊपर आपका टॉर्शन प्रोड्यूस होता है, जिसकी वजह से क्या कहते हैं कि जो भी वाटर कंटेंट रहता है, ज्यादा वाटर कंटेंट रहता है, वो क्लॉथ से रिमूव हो जाता है। ओके, सो there are so many examples related to the torsion, why we torsion use, or what is the application of the torsion. So, so for the introduction of the torsion, I for the introduction of the torsion, I show you a video. Please go through this, and whatever the your question after we, this is the 8 to 10 minute video. You prefer this. After that, we can start the lecture.
A moment which tends to cause twisting is called torque. Longitudinal axis. Longitudinal axis. It is a type of deformation. Torsion is the twisting of an object caused by a moment acting about the object's longitudinal axis. It is a type of deformation. A moment which tends to cause twisting is called torque. A common example of an object subjected to torsion is the transmission shaft, which is used to transmit power by rotation. This could be the drive shaft and axles, used to transmit power from the engine of a car to the wheels, for example, or the shafts used to transmit power from the blades of a wind turbine to its generators. Let's explore what happens when we apply torque to a circular bar. We can see that the applied torque causes the bar to deform by twisting. An interesting thing we can observe is that individual cross-sections of the bar do not get distorted by the twisting. We can imagine that the bar is made up of multiple individual discs, which rotate relative to each other when the torque is applied, but do not deform. This is only true because the cross-section of the bar is axis symmetric. A bar with a rectangular cross-section is not axis symmetric, and so torsion results in warping of the bar cross-sections. This warping is complex, so in this video, we will keep things simple and only consider torsion as it relates to circular bars. Let's fix our bar at one end, and track how a line between point A and point B deforms as we apply a torque to the other end. The applied torque causes the free end of the bar to rotate by an angle phi. This is called the angle of twist. It varies linearly from 0 at the fixed end of the bar to phi at the free end of the bar. We can calculate the angle of twist using this equation. It is a function of 4 parameters: the length of the bar L, the applied torque T, the shear modulus G, which is material property, and J, which is the polar moment of inertia. So, what is the polar moment of inertia? It defines the resistance of a cross-section to torsional deformation, due only to the shape of the cross-section. The polar moment of inertia for a hollow bar, with an outer radius RO and an inner radius RI, can be calculated using this equation. Setting the inner radius to 0 gives us the equation for a solid bar. One neat thing about the equation for the angle of twist is that it gives us a way to determine a material's shear modulus G experimentally. If we apply a known torque to a bar of known length and cross-section and measure the resulting angle of twist, we can use that information to calculate the material's shear modulus G.
You got the topic down? Let's get onto it right now!
5 hours later.
Well, it's been...
Torsion generates stresses and strains within the bar, which we need to be able to calculate so that we can make sure our bar won't fail. To figure out how to calculate these stresses and strains, we can start by observing how a small rectangular element on the surface of our bar deforms. The element is initially rectangular, but when the torque is applied, it gets distorted. Let's take a closer look. Because the bar is axis symmetric, we know that individual cross-sections will rotate but won't get distorted, so the sides CF and DE of the element will only move vertically along the lines shown here. After the torque is applied, the angles of the element are no longer 90-degree angles. This gives rise to a shear strain, which corresponds to the angle you can see here. We can calculate the shear strain by considering only the geometry of the bar and the deformation. It corresponds to this angle between AB and AB prime. We can use trigonometry to derive an equation for shear strain. For small angles, gamma will be approximately equal to the tangent of gamma, which makes it equal to the length BB prime, divided by the length AB. AB is the length L of the bar. We can calculate the length BB prime by realizing that it is the arc length of a circle with a radius r, covering an angle equal to the angle of twist theta. So the shear strain is equal to the radius of the bar multiplied by the angle of twist divided by the length of the bar. This is actually...
Okay, so students, you can see this is the angle of twist. Is what happened. A end is fixed and B end we can rotate. Okay, so B point is rotate theta degree and we get B dash point. Okay, and this gamma will be created. What is the gamma? Gamma is the angle between the axis of the soft and twist. Okay, and this is the twist angle. This is another plane and this in the surface. Okay, so if we want to know what is the value of this gamma, which equal to r is the radius of this cross section, theta is the angle of twist, and L is the length of the soft, or we can say that the length of the specimen. Okay, so go forward.
only an equation for the shear strain on the surface of the bar. But what about inside it? It turns out that the shear strains increase linearly with the distance from the center of the cross-section. So if we define ρ as the radial distance from the center of the cross-section, we can replace r in this equation with ρ to give us an equation we can use to calculate shear strain due to torsion at any point within the bar. That shear strain's...
Okay, now you see this is the shear strain. Okay, so what is the difference between the shear strain and the this gamma factor? Okay, so if we put the sigma. What is the sigma here? Sigma is the stress. Okay, normal stresses. Okay, so in the place of R, if we put the normal stresses, then we get the shear strain here. Okay, and we know the formula or relationship between the shear stress, or we can say the stress and strain. So we get the strain. Now we can easily get the shear stress, because here from this equation we can get the strain. Okay.
Is covered. But what about shear stresses? Like the shear strains, shear stresses increase. What about shear stresses?
Now shear strain is denoted by the gamma and shear stress is denoted by the tau. Okay, so what about the tau? Because if we get the strain, with the help of strain we easily find out the stress. Okay, so continue this.
Like the shear strains, shear stresses increase linearly with the distance from the center of the cross-section, with the maximum shear stress occurring on the outer surface, as you can see here. This is true for a solid bar, but also for a hollow bar. This is useful to know because it means that hollow bars are way more efficient at carrying torsional loads, since the central part of a solid bar is only resisting a small part of the total load. Let's consider.
Okay, there is a good explanation why we go for the hollow soft, कि जिधर भी क्या कहते हैं कि हमको एप्लीकेशन सॉफ्ट वगैरह लेना रहता है तो हम हॉलो सॉफ्ट प्रेफर करते हैं. हॉलो सॉफ्ट क्यों प्रेफर करते हैं? दिस इज द एग्जांपल. अभी आप यहाँ पे देख रहे हैं कि क्या हो रहा है कि ये सॉलिड सॉफ्ट है. सेंटर से आउटवर्ड हमारा जो शियर स्ट्रेस है वो इंक्रीज हो रहा है, ठीक है ना. लेकिन सेंटर पे क्या है कि शियर स्ट्रेस बहुत ही कम है, negligible है. Means we can say that in the center the shear stress is zero. Okay, तो जब shear stress है ही नहीं, then why we waste our material at the center? If there is no stress, then why we waste our material in the center? Okay, क्योंकि यहाँ पे जब stress नहीं है, then we don't need material here. Okay, so we can make this solid soft into the hollow soft and remove the material. So by this action, we can sorry, we can save the material as well as we get a lighter soft. If we remove the material, we can save the material and we get a lighter soft for the use. Okay, so there is the explanation why we go for the hollow soft in comparison to solid soft. Why we go to hollow soft in comparison to solid soft. Okay, so let's play again.
You can see here. This is true for a solid bar, but also for a hollow bar. This is useful to know because it means that hollow bars are way more efficient at carrying torsional loads, since the central part of a solid bar is only resisting a small part of the total load. Let's consider a small element within our cross-section that has an area equal to dA and is located at a distance ρ from the center of the cross-section. The internal force acting on this element is equal to its area, dA, multiplied by the shear stress tau. We can use this information to work out an equation for calculating the shear stresses. The moments caused by the internal forces acting on all of the elements within the cross-section must sum up to be equal to the torque T. Otherwise, equilibrium is not maintained. We can represent that mathematically by this integral. We know that the quantity tau divided by ρ is a constant, because the shear stress varies linearly with the distance from the center of the cross-section. So we can rearrange the terms and move tau over rho out of the integral. It turns out that the integral we now have on the right is actually the definition of the polar moment of inertia. So we can replace it with the letter J, and we can rearrange this to get an equation for shear stress. The shear stress is a function of the torque. To get an equation for shear stress,
Okay, students, now you can see here we take a small component from this soft. We take a small component from this soft, very small element, and we have to find out what is the shear stress of this small element, and we can integrate this to get a full stress on this solid soft. Okay,
we
so
can
for
represent
that,
that mathematically by this integral.
see, this is the integration tau equal
We
sorry
know
t
that the
equal to
quantity tau
0
divided by
to r.
rho is a constant, because the shear stress varies linearly.
See here 0 to r. Okay, if 0 to r is there, then what happen? We can say that it is the means center to periphery. Okay, the minimum value r is 0. सेंटर पे आर की वैल्यू कितनी हो जाएगी 0, और पेरीफेरी पे कितना हो जाएगा, पेरीमीटर पे कितना हो जाएगा, दैट इज दी आर. सो हम कितना इंटीग्रेशन करेंगे, हाउ मच वी कैन इंटीग्रेट 0 टू आर, तो जिसमें आपका होल सॉलिड कवर हो जाएगा. ओके,
Linearly with the distance from the center of the cross section. So we can rearrange the terms and move tau over rho out of the integral. It turns
नाउ टाउ अपॉन रो को क्यों इंटीग्रेशन से बाहर कर लिया गया है, क्यों? क्योंकि ये जो आपका टर्म है इसमें आर नहीं है, सो दिस इज अ कांस्टेंट फॉर दिस इक्वेशन. ओके, टाउ अपॉन रो इज द कांस्टेंट फॉर द इक्वेशन, so we can remove the tau upon rho from the integration.
out that the integral we now have on the right is actually the definition of the polar moment of inertia. So we can replace it with the letter J, and we can rearrange this to get an equation for shear stress.
जीरो टू आर रो स्क्वायर डी ए, ये क्या है आपका पोलर मोमेंट ऑफ इनर्शिया है, क्योंकि अभी हम मोमेंट ऑफ इनर्शिया इसके पहले रीड कर स्टडी कर चुके हैं, जो अब हमारी फर्स्ट यूनिट थी, तो पोलर मोमेंट ऑफ इनर्शिया वहां पे यूज हुआ है. तो पोलर मोमेंट ऑफ इनर्शिया और मोमेंट ऑफ इनर्शिया मींस व्हाट इज द पोलर मोमेंट ऑफ इनर्शिया, इट इज द moment of inertia about the z axis, which is equal to integration 0 to r rho square dA, that is the formula. So we can put the j at the place of the equation.
The shear stress is a function of the torque T, the distance rho from the center of the cross section, and the polar moment of inertia J. It's quite a simple equation.
Ayaka shoulders her family's duty to cherish the aspirations of ordinary people. But she also has dreams.
So we now have equations that allow us.
So now what we can see, tau equal to capital T rho upon j. Okay, so from this equation we can see that tau, which is the shear stress, is directly proportional to the torque and radius. Okay, because means आपका ये जो नॉर्मल स्ट्रेसेस है और टार्क जितना ज़्यादा होगा, जितना ज़्यादा हम टार्क प्रोड्यूस कर सकते हैं, दैट इज द increase the shear stress. Okay, so we can increase the shear stresses by increasing the torque. Okay, capital T here representing the torque. And the polar moment of inertia, आपका polar moment of inertia किसके ऊपर डिपेंड करता है? That is the depending on the area. So area पे डिपेंड करता है, तो क्या होगा कि एरिया जितना ज्यादा होगा उतना ही आपका टाउ और रिड्यूस हो जाएगा. ओके,
Us to calculate the shear strains and shear stresses. We also have the equation for angle of twist that we talked about earlier. These three equations tell us everything we need to know about a circular bar.
okay. So these three equations, shear strain, shear stress, and angle of twist, theta equal to TL upon GJ. Okay. So what is T? T is the torque, L is the length of the shaft, G is the modulus of rigidity, and J is the polar moment of inertia. J is the polar moment of inertia. So when we talk about the circular shaft, then these three equation is the master equations which is required to hold torsion chapter. ओके, जब हमें ये तीन इक्वेशन की ही जरूरत पड़ेगी, वी यूज दीज थ्री इक्वेशन फॉर द होल टॉर्शन चैप्टर फॉर द सर्कुलर सॉफ्ट. तो भी हम सर्कुलर सॉफ्ट की बात करेंगे, देन वी गो थ्रू दीज थ्री इक्वेशन. ओके,
Which is under torsion. So far, we have only talked about a uniform bar fixed at one end with a single applied torque, but shafts are often loaded by multiple torques. This shaft, for example, which is supported by bearings at both ends, is driven by a gear at point B, and in turn drives two gears at points A and C.
सो स्टूडेंट, अभी तक हमने जो देखा, इसके अभी इसके पहले जो भी एक्सप्लेनेशन हुआ कि एक कंसिडरेशन क्या है कि एक सॉफ्ट है जो कि एक एंड से फिक्स है, देन वी कैन रोटेट द अनदर एंड टू जनरेट द torsion. But what happened, there is a many type or multiple type loading condition and multiple type of soft support. Okay, so we see here another type of soft support and generating torque.
It is loaded by three torques. Before we can use the equations for shear stress, shear strain, and angle of twist that we just developed, we need to figure out the internal torque at each location along the shaft. The process for doing this is similar to calculating the shear force along a beam, which I covered in a separate video. First, we draw a free body diagram. Then we make imaginary cuts and use the concept of equilibrium to determine the internal torque at different locations along the shaft. This will give us an internal torque diagram that looks something like this. The maximum shear stress will occur in the section of the shaft with the largest internal torque, and can easily be calculated using the equation we derived earlier. I want to end the video by talking about failure due to pure torsion. If we have two bars, one made of a ductile material and one made of a brittle material, and we apply the same torque to both bars, we will observe that they fail differently. The ductile bar fails at an angle perpendicular to its axis, but the brittle bar fails at a 45-degree angle to its axis. We can explain this by remembering that ductile materials tend to fail in shear, and so fracture along the plane of maximum shear stress. But brittle materials are weaker in tension than in shear, and so tend to fracture along the plane of maximum tensile stress. Moore's circle for pure torsion looks like this. We can see that when our stress element is oriented this way, the shear stresses are at their maximum values, and we have no normal stresses. There is a 90-degree angle on Moore's circle between maximum shear stress and maximum normal stress, which means that normal stresses are at a maximum when our stress element is rotated by an angle of 45 degrees. This explains why brittle and ductile materials fail in different ways due to pure torsion. That's it for
ओके सो यहाँ पे so students, we can see here there is a different failure of ductile material and brittle material. Okay, brittle material is fail like this, and sorry, ductile material is fail like this, and brittle material is fail like this. Then what happened? The brittle material is break due to the tension, and ductile material fail due to the compression and tension combinations. Okay, so now we can start our PPT for the lecture. So students, what I explained in the video, do you have any doubt on that? So here the main focus is why the torsion is produced and how we can rescue the component or save the component from the shear stress or strain. Okay, torsion is nothing but we can say that whatever we see in previous video, but it is the type of deformation. Torsion is a type of deformation. So in particular this diagram, what we can see the first diagram before the torsion. In first diagram, we can see before the torsion, and second diagram after the torsion. Okay, and we already performed the torsion test in the wheel lab. ओके, क्या होता है कि एक स्पेसिमेन लेते हैं और स्पेसिमेन में हम जो हमारा क्या करते हैं, टॉर्शन टेस्ट मशीन होता है, ठीक है, स्पेसिमेन को एक दो जॉ के बीच में फिक्स करते हैं, जिसमें से एक जॉ आपका स्टेशनरी रहता है एंड अदर जॉ इज मूवेबल. तो रोटेट होता है पर्टिकुलर डिग्री पे। तो क्या करेंगे कि हम जो स्पेसिमेन है which is actually a circular rod, and we draw line a straight line in the surface of the circular rod or specimen, and we can fix this rod at the torsion machine, and we apply the torque. Okay, so what happen कि आपका जो मटेरियल है, जो भी रॉड है, वो ट्विस्ट हो जाएगा। तो हम ये देखेंगे कि जो लाइन हमने ड्रॉ किया था वो कितना ट्विस्ट हुआ। ठीक है, तो फ्रॉम हियर व्हाट इज द rotational deformation, what is the rotational deformation which is responsible for the shear strain, and what is the twist of angle we get
Sure.
from the, yes,
Sorry, sir.
any question? Okay, okay, so what is the twist of angle? Okay, तो यहाँ पे हमको जो 3 मेन फार्मूला है वो हमने लिखा, shear stress, shear stress and angle of twist for the circular shaft। तो ये जो है यही आपके सिलेबस में है। सर्कुलर शाफ्ट इज योर सिलेबस इन द टॉर्सन चैप्टर। ओके, तो डायग्राम में इजीली हम देख सकते हैं व्हाट इज द टॉर्शन, torsional deformation of circular shaft। Okay, now we can see that here torsion is the moment that twist or deforms a member about its longitudinal axis by the observation if angle of rotation is small, length of shaft and its radius remains unchanged। यहाँ पे क्या दिया है कि एंगल ऑफ रोटेशन बहुत स्मॉल रहेगा तो लेंथ में, शाफ्ट के लेंथ में कोई भी चेंज नहीं होगा। Now, what is the definition of this shear strain is? See here, ये देखिए सेम क्या होता है कि जब भी हम कोई फार्मूला ड्राइव करते हैं तो क्या होता है कि हम पूरे होल कंपोनेंट के लिए कोई फार्मूला ड्राइव ना करके एक जो भी कैलकुलेशन रहता है वो हम एक स्मॉल कंपोनेंट के लिए करते हैं। ओके, ये स्मॉल कंपोनेंट के लिए करते हैं, दिस इज ए स्मॉल कंपोनेंट, ठीक है ना। और उसके बाद इसका जो भी रिजल्ट रहता है, व्हाट एवर द रिजल्ट ऑफ दिस स्मॉल कंपोनेंट, वी जस्ट इंटीग्रेट दिस and we get the total strain for the whole component, for the whole component। Okay, so here this is gamma, and what is the gamma? See here, let's delta x tends to dx and delta phi tends to d phi, ठीक है ना। डी डी डेल्टा है और ये डी है। डेल्टा, व्हाट इज द मीनिंग ऑफ डेल्टा? डेल्टा बहुत ही स्मॉल क्वांटिटी को रिप्रेजेंट करता है या फिर डिफरेंस को रिप्रेजेंट करता है। ओके, तो डेल्टा जो है उसकी जगह पे हमने डी कर लिया है, यहाँ पे भी देखिए डी कर लिया है। ओके, नाउ डी बी, नाउ डी बी इक्वल टू रो डी फाई इक्वल टू डी एक्स गामा। तो यहाँ पे आपका क्या कहते हैं, What is the equation? Now, gamma means shear strain is equal to rho d phi upon dx. That is wrong. D phi upon dx. Okay. Since d phi upon dx equal to gamma upon r, and now where the this strain is maximum, ये आपका स्ट्रेन मैक्सिमम कभी होगा जब ये आउटर सरफेस पे होगा, मींस आर की वैल्यू जब सबसे ज्यादा होगी, आर की वैल्यू सबसे ज्यादा कभी होगी outer surface पे, which is denoted by the c. C is nothing but the radius of the circular shaft. Okay, so we can see here gamma equal to, from this equation we get the tau upon rho max, sorry, rho upon tau max. Now for the solid shaft, shear stress vary from the zero at the shaft longitudinal axis to maximum value at the outer surfaces. Okay, so due to the proximately of the triangles are using the Hooke's law. What is the Hooke's law here? Equation now. Tau equal to rho upon c tau max. Tau equal to rho upon c tau max. Or tau equal to tau max upon c integration to area. Now what is this? We can say this is the polar moment of inertia, which is we already observed in the which is we already discussed in the video. Okay, so we can convert this equal to j, and whatever the equation we get here, tau equal to tau max upon c into j. What is the j? J is the polar moment of inertia, which is we observe in the moment of inertia chapter. Now, see here the longitude, sorry, the integration in the equation can be represented as the polar moment of inertia J of soft x section area compute about its longitudinal axis. So tau max Tc upon J. See here tau max tau C divided by J. From this equation we get this equation. Now tau max, what is the tau max? Maximum shear stress in the shaft at the outer surface. T resultant internal torque acting at the x section from the method of the sections and the equation of the moment. Equilibrium applied about the longitudinal axis. Okay, J is the polar moment of inertia at the x sectional area, and C is the outer radius. Okay, outer radius of the shaft. Okay, now we talk about the torque. Okay, twisting moment are the torque or force acting through distance so as to promote rotations. See here, what is the example for that? Using a wrench to tighten a nut in the bolt. ठीक है, हम wrench यूज करते हैं ना बोल्ट को टाइट करने के लिए, अगर वहां पे क्या कहते हैं कि दिस इज द एप्लीकेशन ऑफ द टॉर्क और टॉर्शन, ठीक है ना, वहां पे हम क्या कहते हैं कि टॉर्शन के थ्रू ही ये पॉसिबल होता है कि एक नट बोल्ट में टाइट हो पाए. दिस इज द एग्जांपल ऑफ टॉर्शन. ओके, नाउ wrench and force are all are perpendicular to one another. The moment is the force F times the length of the wrench. Simple torque T equal to F into I. What is the F? F is the force and I is the moment of inertia. Okay, and see here, this is the range, the example of. So we apply the torque. This is the screwdriver, and जब भी हम screwdriver को tight करते हैं या loose करते हैं, then we also use the torsion application. Okay, torsion is the twisting of a straight bar when it's loaded by the twisting moment or the torque that tend to the produce rotation about the longitudinal axis of the bar. For instance, when we turn a screwdriver to the produce torque, our hand apply to the torque to the handle and push the shank of the screwdriver. Okay, तो जब भी कोई भी स्क्रू हमको टाइट करना है या लूज करना है, then there is the application of the torsion. Now bar subjected to torsion. So यहाँ पे सेम टेक्स्ट रिप्रेजेंट कर रहे हैं. See, let us consider a straight bar. This is the straight bar. Okay, support at the one end and acted upon by two pair of the equal and opposite force P1 and P2. ठीक है ना. तो यहाँ पे क्या कहते हैं कि ये एक एंड फिक्स है, लेकिन हम जो टेस्टिंग करने जा रहे हैं वो यहाँ पे एक हॉरिजॉन्टल ये हमने लगा दिया, सॉरी एक वर्टिकल बार अटैच कर दिया है और यहाँ पे वर्टिकल बार अटैच कर दिया है क्योंकि हमको टॉर्क लगाना है. ठीक है ना. तो यहाँ पे हम P1 फोर्स लगा रहे हैं क्लॉकवाइज डायरेक्शन में और यहाँ पे एंटी क्लॉकवाइज में P2 फोर्स लगा रहे हैं. तो इसकी वजह से क्या हुआ कि टॉर्क क्या हो जाएगा, T1 देखिए, T1 कितना हो जाएगा, P1 इंटू D1 दिस डिस्टेंस, P2 इंटू D2 दिस डिस्टेंस. ये आपका जो दोनों टार्क है वो इक्वल टू ईच अदर. So here then we can write the moment as T1 and T2. Okay, see T1 this side and this side. Now whatever the torsional loads on the circular shaft. Okay, so student, I stop my lecture here. So now this is the question answer time. If you have any doubt, then ask your question.